Okay, I'm going to finish with a couple of examples about how to use the gain margin and the phase margin. But first I wanted to remember what we learned about with the root locus. So we know that if the number of poles minus the number of zeros is greater than 2, then we can say that there is a gain k that makes the closed loop poles cross the imaginary axis. Or, in other words, we just say it a different way. The closed loop poles are in the right half plane for some k. Okay. For the Bodhi plot, if we think about a single pole, so if I write that in terms of the frequency response, 1 over j omega over p plus 1. If we write the phase angle of this thing, it goes to minus 90 as omega goes to infinity. So at large frequencies, a pole will contribute minus 90 degrees of phase, and if we have a 0, the angle contributed by that 0, whoops, I should write it as, I'll write it as z here, just so it's very clear. That goes to plus 90 degrees as omega goes to infinity. Okay? So hopefully you can see that what this means is if the number of poles minus the number of zeros is greater than 2, then the phase angle of g of j omega will go to minus 270 degrees or more as omega goes to infinity. Right? So if we had 3 excess poles, then we have 3 times minus 90 is 270 degrees. If we had 4 excess poles, then we have 4 times minus 90 is minus 360 degrees. And so the way that we can interpret this in terms of stability, there's always a point where j omega it will cross through minus 180 degrees at some frequency. Okay? So let's look at a couple of examples and we'll see how this works. So the first example I have here is g of s is 100 over s times 1 plus s times 1 plus 0.0125 times s. And so we can see that there are 3 excess poles, no zeros. And so the phase angle goes to 3 times minus 90 degrees, which is minus 270. As omega goes to infinity. And so what I did was I made the Bodhi diagram here. I used a command called margin in MATLAB. And what this does is it produces the Bodhi plot, but it also tells me the gain margin and the phase margin of the Bodhi plot. And it's sort of hard to read it here, but it's showing here the gain margin, and it's also showing the point where the phase is crossing through minus 180 degrees. So that phase crossover frequency is 8.94 radians per second. Okay, so that's this little dotted line over here. See, the dotted line here is at minus 180 degrees. this dotted line is indicating where the phase plot is crossing through minus 180. And if you look at the phase, it actually starts at minus 90 because this thing has a pure integrator, so the phase starts at minus 90, and it goes down to minus 270 degrees, just like the little calculation here said. And where it crosses through minus 180, that's at about 9 radians per second. And the gain at that frequency is 1.83 dB, and that's greater than 0 dB. So this thing is unstable. Okay, this plant is unstable. And the gain crossover frequency is this little dotted line. It's awfully close here. It's 9.93 radians per second. And the phase there is minus 181.33 degrees. And that is more negative than minus 180 degrees. So again, we see it's unstable. The phase margin here is actually a negative number. It's minus 1.33 degrees. And now I have a couple of examples of systems that are actually stable, and I took these from a data sheet from an op-amp. It's from an OPA 227 op-amp. And here they've plotted the gain and the phase frequency response on the same plot. So we have frequency in hertz along the x-axis, right? It's log scale, 10, 100, 1 kilohertz, all the way up to 100 megahertz. And then the axis over here, the first y-axis, is the gain in decibels, and they call it AOL. This is the open loop gain. Okay, so that G I'm going to read against this left y-axis, and the right y-axis is the phase versus frequency. And so that's this little phi versus frequency here. And so to find the gain crossover frequency, I'm looking for the point where the gain crosses through 0 dB. So I follow along here, and it's right about here, which is about 9 megahertz. Okay, you can see it's crossing through. This line is the gain line, and it's crossing through 0 dB at 9 megahertz. And so if we want to find the phase margin here, we look for how far, it turns out this line is also where minus 180 degrees is. And so we draw a line from where the phase curve is to where the minus 180 degree point is. And so I've got here that the gain crossover frequency, it's about 9 megahertz. Sorry, I shouldn't write it as an omega. I'm going to write it as F, okay, because I'm talking about frequency in hertz. And the phase angle there, if you look at it, it's about 130 degrees, or minus 130 degrees. Okay, so the angle G omega at 2 pi F, right, so I'm using omega here. That's about minus 130 degrees. And so the phase margin turns out to be 180 degrees minus 130 degrees, or 50 degrees. Okay? And if that equation doesn't make sense, just think about the fact where it's the amount that the phase, it's the difference between minus 180 and the actual phase here. So this is 50 degrees. That's the phase margin on this guy. Okay? And the gain margin is what the gain is at the point where the phase is crossing through. I'm going to use red for this. So the phase here is crossing through minus 180 up here, and we can see the gain is now below 0 dB. And so the gain margin, again, we're going to read it against this axis, right? It's easier to draw the lines this way. Okay, so the gain margin is here, and that turns out to be 10 dB. Okay, because the gain is minus 10 dB at the frequency where the phase is crossing through minus 180. Okay, and that frequency F, the phase crossover frequency, is just about 20 megahertz. Okay? So one last example, this is an OPA 227 op amp. I took another one here. This is called an uncompensated op amp. It's an OPA 228, so it's exactly the same op amp, but you'll see there's a difference in the phase response here. So again, same idea, gain and phase here. But now if we look at the gain crossover frequency out here, here's the gain crossover frequency at 10 megahertz, and look at where the phase is there. It's about at 160. So, okay, the frequency where the gain is crossing through 0 dB is 10 megahertz, and the phase margin is only about 20 degrees here, right? Because the difference between minus 160 and minus 180 is 20 degrees. And the gain margin, well, it's not so obvious here because we can't see where the phase, here's the phase plot, it actually doesn't go, it's not drawn out to minus 180. But the gain margin is going to be similar, right, to the previous one. It's going to be probably about 10 dB, okay? So the difference between these two op amps is one of them has a 20 degree phase margin, and the other one has a 50 degree phase margin. That's what this thing is here, 50 degrees. And usually, we're going to talk about this in the next couple lectures, but we'd like to have a phase margin of about 45 degrees or 50 degrees to have a system that has the right kind of transient response without a lot of overshoot and oscillation. Okay? So that's all for this time, and I'll see you on Friday.